Hello everyone! Welcome to this workshop on object detection with deep learning. My name is Kenza Yusfi and I am a member of the Teaching Assistance team in Code Labs Academy. I will be presenting today's workshop and help you get the most out of it. I hope you are ready to learn, so without further ado, let's get started. We have divided this workshop into two parts, and you are going to see that they aren't equal either in terms of time or size. The first one is a theoretical part where we'll go step by step for you all to understand what object detection is and all the lingo around it. And in the second part, we are going to see an overview of a practical example, which is YOLO v5. Let's start with a brief definition of object detection. As you can read on this slide, object detection is a computer vision technique that allows us to tell what objects are in an image and where they are located. So the first highlighted word is computer vision, and that means that object detection is part of the field that aims to give computers the ability to see by using visual content as input, for example, images and videos. And then the second and the third highlighted words are what and where, meaning that it has to identify what objects are in an image and where is their location on it. As we can see on this example image, where we have 4 boxes drawn around the places of the animals, and on top of each box we have a label telling us what animal it is. So in here we have either a cat or a dog. And when it comes to this slide, we have 2 different examples, but only one of them represents what we want from object detection. So if we follow the previously mentioned definition, in object detection we have information about what objects are in an image. And this characteristic is present on both examples. So the first one is telling us that it's a plastic bottle, and so is the second one. However, the second part of the definition that we saw just now mentions that object detection also tells us where an object is located in an image. And in here, only the second image localizes the object. So it is an example of object detection. And if you're curious, the first image could be an example of image classification, where the goal could be to recognize an object in an image, or to be more precise, tell us what this image represents. So usually when you get started with computer vision and deep learning, you will get to classify images as your first task. And one of the most popular examples in image classification could be telling whether an image represents a cat or a dog, through the cats versus dogs dataset, or what number is represented in an image, for example in the infamous MNIST dataset. Of course, you will notice through this workshop that we will go back and forth to classification, from and to classification, because it helps us understand detection better. Now you could be wondering, why do we need object detection? Sure, it's fun to create models that detect animals, people, or anything else really on an image, but what are its application and uses? And the answer to that is that there are actually many uses. The most important and popular ones are self-driving cars, video surveillance, and object counting. For self-driving cars, you can probably guess that detecting cars and pedestrians around is more than necessary to avoid any collisions or accidents. And with object detection, it can also be easier and faster to follow people's movements in crowds, in crowded places, and monitor that every activity is normal. So for example, that no one is in need of medical assistance or help. And of course, you have to know that object detection is only the basis of these fields. When it comes to the second image, for instance, we are not only detecting people, but we are also tracking and following their movements. And that's actually a whole other topic. Another thing to keep in mind is that for a number of companies, there could be a different way to use object detection and also a different purpose, but the concept and the general purpose stays the same. And one popular example that you may have come across before is the Amazon Go initiative by Amazon, obviously, where the main idea is to have markets without any people or help to scan the products you buy. So you would walk into a store, scan your phone at the entry, and you will be tracked by hundreds of cameras set on the ceiling, responsible for sending images of you, taking products, adding them to your cart, or putting them back in, and then you would simply have to leave the store and you will receive the receipt on your phone. Once again, object detection, object and person detection are only the basis of this whole concept. Now that we have an overview of what we want to achieve with object detection and why we need it, let's go over some basics and general information before diving into technical details. Here is another case where we want to go back to image classification to better understand what object detection is. So in image classification, we have a set of images and we want to identify to which class each image belongs. So let's just imagine that we have, for example, a dataset that contains images of plastic bottles and cans, and we want to classify to which class each image belongs. And so in here, what do we have as information? We have our images and also the labels or the classes to which they belong. So for each image, we have a certain class to which it belongs. But of course, this isn't enough information for object detection because in addition to identifying the objects on the image, we want to localize them. And we are going to do this with what we call bounding boxes. So bounding boxes will allow us to localize the objects on the image. And they are the boxes that we saw earlier drawn around the cats and the dogs. We can represent them as shown on this image on this slide by 4 digits or 4 numbers A, B, C, D, and this representation varies from a model to another. Let's see some of the most common ones, for example. We have one bounding box representation where we take the coordinates of the pixel at the top left corner of the box and then the bottom right corner of the box, and then we can deduce the 2 other points in our code. The second representation is to take one of the tops. So for example, in here we take the top left one and then we add as information the height and the width. And the last representation is to take the center, so the coordinates of the center of the box, x, y, and we add as information the height and the width. For example, in the center representation, we would have this vector to identify or to represent each bounding box that we would have detected. PC is the confidence score, and it's basically a probability that tells us how certain the model is about this detection. BX and BY are the center coordinates of the bounding box, as we saw earlier. BH and BW are the height and the width of the bounding box, and C1, C2, and C3 vary. So we could have C1 and C2, we can have 5 classes. So it basically varies according to the number of classes, and in here it says that it is an example where we have 3 classes. So if, for example, we have this where we see the last 3 values are 0, 1, 0, that means that our model detected that this object belongs to the class number 2. And if it was 1, 0, 0, so C1 will be at 1, that would mean that this object belongs to the class number 1. Let's once again go to our plastic bottles and cans in classification. So if during the training our model makes a mistake and the first image would be classified as a can instead of a plastic bottle, so it would predict that it belongs to the class number 1 when it should have predicted that it belongs to the class number 0. How would we know that it made a mistake? Well, it's pretty intuitive and simple. We would simply compare the 2 labels and we would see that the output is wrong, so the detection is wrong. But now we want to generalize this to the bounding box. So how do we tell if our prediction is correct or not? This is the next question we are going to answer with the concept intersection over union. Let's suppose that we want to detect cars, and in this image our model would output the prediction in red, while the correct detection should be the bounding box in green. So in order to measure how good our prediction is, we will have to first calculate the intersection, and then the second step would be to calculate the union. And then simply, as the name states, we would do intersection over union. More precisely, we would divide the area of the intersection by the area of the union, and this value will be a value between 0 and 1 because the intersection is always smaller or equal to the union. Let's see an example of this calculation of intersection over union. In this first example, the intersection over union will be around 1 out of 4, which is 0.25, while in this second example, which is a little bit closer to the truth or more correct, it will be around 3 out of 4, which is 0.75. So in here we can guess that the closer the IOU is to 0, the worse it is, and the closer it is to 1, the better it is. And this is why we sometimes introduce a threshold to our IOU. Most of the times it is around these values. So if it is greater than 0.5, we would say that it's a pretty decent detection. If it is over 0.7, it will be good. If it is over 0.9, it is great or nearly perfect. But of course, this depends on your model and what do you want to do with it. We now move to a quick remark that I want to give you, and it is the one written on the slide. So object detection is about finding what and where multiple objects are in an image. And actually, this highlighted word introduces a new challenge, or at least the biggest challenge of object detection. Let's assume that in object detection, we only have to detect one object in an image. That would mean that the output of our model would be the class of the class of the object detected, the coordinates of its VBox, and all the rest of the vector that we saw earlier, so the score, the confidence score, and the one-hot encoding of the classes. However, it all becomes tricky once we have to detect multiple objects. So as we can see in here, if we had to detect all of these horses, our model would have to output as many vectors or as many bounding boxes as there are objects. And beforehand, so at the beginning, our model cannot know how many objects is it going to detect. However, this information, which is the size of our output, is a key information when we build our model, and it can't be variable. The dimension of the output of our model is, as you can see, a big challenge, and it was the core of the research in object detection for a few years now, and we are going to go through a few solutions that were proposed, starting with the first ideas, which suggested considering one image as many. So if you are wondering how that is done, we are going to see some examples. The first one we'll go through is called sliding windows. Basically, we would have a box that determines which part of the image we are going to work on, and in itself, this box will be considered as a new image. And of course, you should note that the boxes in this case are called windows, and you shouldn't confuse them with bounded boxes, as those localize the object, and the windows tell us which part of the image we are going to. A little bit more detail on this. So for each of these windows, we are going to take the window region and apply an image classifier to determine if the window has an object that interests us or not. So for example, in this third image, we have part of the car that we might classify as a car if our model is interested in detecting cars. And that is how, with each image, we are having some kind of sub-images to process. You could probably guess that slide-in windows weren't exploited much, and the reason behind that is that they require a lot of computations, because as you could see, we are cropping out so many regions of the image and running each of them independently through a convnet or a classifier. And that's why the next set of algorithms appeared. The main thing we were concerned with was reducing the number of regions to process. This time, rather than sliding a window through the picture, they tried to group similar pixels in an image to form a region, and then this region would then be fed to a classifier to identify the class that it presents. So, for example, in this image, us as humans, we can see that it contains 3 main areas. So we have the background, which is the grass, and then 2 others, which are the dogs. So the purpose of the new algorithms was to try and group together the places of the image that contain the same characteristics and traits. For example, when it comes to color or texture or size. And one solution that stood out was selective search. And it is also based on group in similar regions, based on color, texture, size, and shape. And then these regions that we get from selective search, we would then feed to a classifier and then classify to which class each region belongs to. And from there, we could detect our objects. After it, RCNNs were introduced. They proposed a method where we would use selective search to extract around 2,000 regions from an image, and these regions were called region proposals, and we would classify them as we saw earlier. So for each region, we are going to use a convnet to classify to which class it belongs. Then RCNNs were largely improved by new architectures like fast RCNN, faster RCNN, and mask RCNN. But as you can notice on these architectures, all of them were what we call two-stage solutions. And this means that we have the part that proposes regions and then the part that classifies the objects in these regions. And of course, this was something we wanted to improve on or make a little bit better by using only one stage. And that's when proposal-free solutions appeared, and they contain only one stage instead of 2. So for example, we have SSD and YOLO, and we are going to focus in today's workshop on YOLO. YOLO stands for You Only Look Once, and the idea behind it is that we would have an image that we would feed to our network, and we would get the detections as an output, without having to propose regions and then classify them. To understand how YOLO works, I suggest we go first to what we want from YOLO. So to start, we will have our image split into a grid of size S by S. On the slide, for example, we are dividing the image into a grid of size 3 by 3. And in YOLO, one remark is that it uses the center representation for B boxes. As you can see in the black vector, we have PC, which is the confidence score, BX and BY, which are the coordinates of the center point of the B box, and then BH and BW, which are the height and the width. The first idea is that each cell of the grid will return a representation of one B box. Let's take a look at the example again. The first top 3 cells all will output one B box, but in this case, because all of them don't contain an object, they are going to output a vector with the confidence score 0, which means that there is no object detected in them. And when it comes to the 6 bottom cells, you can notice that all of them contain a part of the white car. However, only one will be responsible of representing it, and it will be the one that contains the center of the car. So, it will be, for example, the one in the center. By doing this in YOLO, one problem we are solving is the dimension of the output of our model. So, because we say that each grid cell is responsible for one B box, we can define the size of our output. So, in this case, we have a 3 by 3 grid, which means that we have 9 grid cells, and each one of them is responsible for outputting one vector. So let's just assume that a vector contains 8 elements, as it is the case in this example, but of course it can go higher if we have more classes, so for example C1, C2, C3, and C4, or lower if we only have, for example, only 2 classes. And that means that we have solved the challenge of the dimension of our output. One other concept that I want to tackle is called non-maximum suppression. And this happens whenever we have overlapping B boxes. That means that one person, for example, on this slide, will be detected many times. So what we want from this is to get rid of the worst representation of the person. And the way we are going to do that is by using this concept of non-maximum suppression. So the first step to it is to calculate the IOU between the highest scoring B box, in this case it's the one with 98% confidence score, and the one right below it, so the one with 80% confidence score. And if that IOU is bigger than a certain threshold, so for example 0.6, 0.5, it depends on your model and your case, we are going to drop the second one. And then we continue to do this with all the overlapping B boxes, so it will be between the one with 98% confidence score and the one with 76, and if it is once again bigger than that threshold, we are going to remove the second one. This is the YOLO timeline. So YOLO has known multiple versions. The first one and the original one was in 2015. Then we had a few other versions till the ones in 2020, which were YOLO v4 and YOLO v5. We are going to look at YOLO v5 in general. So here is the architecture of YOLO v5, simplified of course, and you can notice that it has mainly three parts: the backbone, the neck, and the head. So the model backbone is mainly used to extract important features from the given input image, and then when we extract those features, we are going to move to the neck of the backbone, to the neck of the model, where we mainly generate what we call feature pyramids. And the goal of these feature pyramids is to detect elements at different scales, meaning that even if the object is small, it will still be detected, and same if it is larger. And then the last part of our architecture, is called the head. And the head in here is mainly used to perform the final detection part. It applies anchor boxes on features, and it generates the final output vectors with class probabilities, objectness scores, and bounding boxes. And this part of YOLO v5 is the same as, it is called YOLO layer, and it is the same as the one we find in YOLO v3. So now we are going to see an overview of YOLO v5. What we have to do is Google YOLO v5 and head to the first GitHub link. So it's going to be the repo for the code. You can find in here some documentation on the code and how to use it. So for example, tutorials. You can also have tutorials for training it on custom data and on how to get best training results. But because we are going to see only a surface of this and only an introduction, we're going to head to the Colab link, which I already have opened here. The first step is to clone the repo in your space, which we can then find in here. It contains mainly 3 directories. So for example, in utils we have a few files which we can understand in general, for example the activations. We also have the activation functions. We also have the data augmentation file for data augmentation. We have data loaders to load our data, and we also have the metrics. So for example, in metrics we can find IOU, I believe. For example, this is one implementation for it, which you can check out on your own. And then other than utils, we have models. So in models, you can see that there is not only one YOLO v5, but multiple versions. And these versions vary in the number of parameters and how complex they are. And today we are simply going to try out the YOLO v5s, which is the smallest one, just for it to be a little bit quicker. but of course you can try any one you'd like. And after this, we have the directory for our data. So we have the directory for the images we are going to use for detection. So these ones come with the repo. We have this first image which is like a bus with a few people. And we also have the second image of Zidane. And so we see that there are 2 people in here as well. 2 people. And for the detection, we are simply going to go to this inference part. We already have the code, so this part I am going to cut because it simply displays the result. I'm just going to write it again here. So if we use this line as it comes in the repo, it says that the source of our data will be in data images, so it's going to take these 2. And as we can see in here, so this tells us that we can use a directory as a path. We use the weights for YOLO v5s, as I said, and this will be the image size, and this will be the image size. So we're just going to run this. So we load the weights of YOLO v5s, and we're going to have a little bit of a summary of this detection. So it says the number of layers that it used and the number of parameters, and it tells us what it has detected in both images. So in bus, we have detected 4 persons and 1 bus, and in the second image, we have detected 2 persons and 2 ties. So we're going to try and display the result, and it says in here that the result is saved in runs/detect/exp, which is this one. So we're just going to, so if we refresh in here, we're going to find it. Sorry, here it is. So runs, we have in here exp, the 2 images of the detections. So here is the first detection. As you can see, it has detected the 2 people with 2 different confidence scores, as well as the ties. And if we go to the second one, which is bus.jpg, once again, here is the detection. Let's now take a look at another example, which we are going to choose on our own. So as you can see in here, you can have images, you can have videos, you can specify a directory and all of the files in it. You can have a video link, as well as simply saying which files are you specifically interested in. So let's just so this is the image that I chose. I just found it on Google. So as you can see, it contains bicycles and people, and we are going to try the detection on it. So it's called bicycle.jpg. We run the cell again. We're going to load the same weights, and this is the summary, and it says that it has detected 3 persons, 3 bicycles, and 4 backpacks. Let's see the results. So it says that it has been saved in exp2. If we check in here, so we refresh. Here it is, so exp2, and it's called bicycle.jpg as well. And here is the detection. As you can see, it's pretty accurate. I didn't even pay attention to the backpacks when I mentioned it, for example. And here we have the detection of the backpacks, as well as the bicycles and the people. And that is it for the overview of YOLO v5. Thank you all for your attention, I hope you appreciated this introduction to object detection. I would advise you, if you want to go further in object detection, to check each of the concepts that we have learned or seen today and go a little deeper in it to better understand it and try to implement each of the concepts. So for example, IOU, non-maximum suppression. Take a look at the models that we have mentioned, such as RCNN and YOLO and also STD. As you know, this workshop was brought to you by CodeLabs Academy. CodeLabs Academy is an online learning platform that offers highly interactive learning. It offers a variety of learning methods as well, such as workshops and bootcamps. When you enroll to a bootcamp, you get access to one-on-one career coaching on top of the access to all the educational content. You will also have the liberty of going through the learning content at your own pace. If you can't pay now, we offer a deferred payment schedule. You can choose to pay our program tuition over 5 years, and if you choose to pay upfront, you will get a 500 euros discount. Our next bootcamp for data science starts on July 9th, 2022, and the application deadline is on June 25th of 2022. But of course, we will still have other bootcamps, not only data science, after that date. So stay tuned. Goodbye, everyone.